Okay, I hope the screen is visible to all of you.
Yes, sir.
Okay, so so okay, this is yeah. So we'll start. So good evening, everyone. Welcome to this sixth tutorial session of on the course of materials characterization. I'm Sabyasachi Panda. So let's begin the session. So in the last class, what we have gone through is that we have seen different kind of contrast mechanism, as well as we have seen also different imaging modes and its operation of scanning electron microscopy. So today we will go through a few of the other contrast mechanism, like how these mechanism are produced and what are their significance towards the relation and the features of different samples, and how we can use them to our to viewing our samples. Okay, so in the last class we have gone through two of the contrast mechanism. One is topographic contrast, another one is compositional contrast. Okay, so these are the two primary contrast. When I am talking about any kind of contrast mechanism in scanning electron microscopy, so these are the two important and primary contrast mechanism that I want to see. Like, so that is why they are also related as these are the strong contrast mechanism. Compositional contrast comes when I have different phases present in my microstructure, or when I have different atomic elements present in my microstructure. That means my Z variation, if my in my sample it is there, then the compositional contrast will come. And topographic contrast comes when different kind of instead of a flat surface, when there are different kind of features are there, like pores, like fractured surface, all those things when all are present in my sample, then I will get uh, then I will get topographical contrast. So these two are the primary contrast mechanism. And in this, I think in the last class we had a doubt that how the electron, like scanning electron scan in a scanning electron microscope, how the secondary electron and backscattered electron. So these are the two primary electrons beam we knew. So one is secondary electron, another one is the backscattered electron. So this is a typical example of the detector system. Okay, and this detector system is generally we know it as ET positively. Just wait a second. ET positively biased detector system. So here the ET stands for Everhart Thornley. So ET detector, last time in the last class we have gone through a few of detectors. Just to remind you, ET detector was one of them. Then another detector is TTL detector, which is through the lens detector. Then another one is BSE, only dedicated for BSE detector, is solid state detector, which operates on the mechanism of diode PN junction mechanism. And there was also another detector called BAC to AC, that means backscattered electron to secondary electron conversion detector. So these detectors are there. So but this detector which I am talking about, this is a ET, that means Everhart Thornley positively biased detector. So why positively biased? Because here you can see in this portion that a positive potential is given, right? Plus 300 it is written, and so a positive potential it is given. Why positive potential? Because all the secondary electrons which are coming out of my samples, they will be negatively charged. Since they will be negatively charged, but their charge amount is very you can say minus within minus 50 volt. So by applying a voltage or a potential of plus 300, not very large potential, but potential of plus 300, these all AC will be uh, going to my detector. So this is my detector system. Okay, and this is my incident beam, if I am talking about. So this is a typically one of the cross section of the ACM. And here you can see one interesting phenomena, that all these BAC which are going here, all these BAC which are coming out of the sample, after colliding with either the pole piece here or with any of the instrument in the chamber, any of the part in the chamber, they are getting converted into AC. That means that is those kind of conversion. For those kind of conversion, we have a special detector called BAC to AC detector. So this conversion also, after the from BAC to AC, when they convert those AC, that means the secondary electrons also will be captured by this detector, right? So this is a typical detector system in a scanning electron microscope. Okay, so since the amount of secondary electron and the amount of backscattered electron are coming is high, so that is why we can easily differentiate between a topographic contrast or between a compositional contrast, and that is why these contrast mechanisms are known as strong contrast mechanism. However, now keeping aside these two contrast mechanisms, there are different type of other mechanisms also are present, but they are not as strong as these two, topographic contrast and compositional contrast. They are weak contrast mechanism. If we want to and though these mechanisms do not occur in every crystalline solid or every amorphous solid, that means they do not occur in each and every, generally we cannot visualize those contrast, but in a certain class of solid or a certain class of materials, to be in general, we will be able to see this kind of contrast. And those contrast, to see those contrast, we have to make sure that the strong contrast mechanism would be as low as possible. When your strong contrast mechanism is present, you will not see this weak contrast mechanism. To see this weak contrast mechanism, you have to make sure that your strong contrast mechanism, that means topographic contrast as well as compositional contrast, has to be as low as possible. And why this weak contrast mechanism arise? They arise due to electric field in the sample and magnetic field in the sample. Okay, and they do not, you cannot see them in general, but in a particular solid or in a particular type of structure. Okay, and since we can see only in a particular solid and a particular structure, we will see why in a particular solid we are seeing. So these actually, when we see the contrast based on this mechanism, we will get some information on specimen electric field or specimen magnetic field as well. Okay, and generally we to view this kind of contrast mechanism, we use the thermionic source, that is tungsten or lab 6. So these are the two, because using these two we will be able to produce high current operation we can do. Okay, so these are the thermionic source that we use to view the weak contrast mechanism. Now we will see in certain type of solid or certain type of structure how this weak contrast mechanism is affecting our microstructure. In a general microstructure, we might or we might not be able to differentiate when the strong contrast are present, but let's assume for a time that this strong contrast mechanism we are not able to, we have minimized as much as possible. Now what are the let's say my topographic contrast I am talking about, my element is completely flat. There are no fracture surface, it is completely flat, it's a pure element, so no chance of compositional contrast is there. But still, if I see some white and black region, then what might be the possible explanation for that? For those kind of scenario, we have to view a weak contrast mechanism. Okay, so first coming to the contrast mechanism by electric field. Why this electric field why this electric field is producing the weak contrast mechanism? And remember, this weak contrast mechanism by electric which is being produced by electric field is seen only in case of the insulating materials or a few engineering structure, right? Why? But in this case, like insulating materials or engineering structure, why this kind of contrast is coming? Let's say my sample is like this, okay, and incident beam is coming. So this is my specimen and this is my incident electron beam, and here I have given some amount of positive potential. Let's say I have given 300 volt, right? And this distance which I am from my sample here, all these ACs will be coming out. I'm assuming that all the ACs are coming out. Okay, so this distance typically is kept around, let's say, 5 centimeter. This sample, so this is my sample. If I'm talking about, this is my incident electron beam, and these ACs are coming out from my sample, and here is my detector system, right? So when this kind of interaction happens, so let's say this 5 now the distance is 5 centimeter and the voltage or the potential I have applied is 300 volts. So if I have to calculate the electric field, so electric field is voltage divided by distance. So in this case, between this entire system, if I am talking about this entire system, my electric field will be, let's say, 300 divided by 5, so 60 volt per centimeter. This I am talking in terms of a large scale. Okay, so if I am talking in terms of, if I am taking consideration into this whole picture, then 60 volt per centimeter, and generally with this 60 volt per centimeter, positive 60 volt per centimeter electric field, if I am applying, then all these scanning, all these secondary electron, they are, I can extract many of the secondary electron. That means my delta secondary electron yield will also increase in general scenario. But now let's take aside, keeping aside this general scenario, when we are talking, now let's see in another case. So the electron beam is coming, right? And when this electron beam is coming, it is hitting a very, I'm now considering only one incident beam, right? Not like many incident beam. I'm talking in terms of one incident beam. So one incident electron beam is coming right here, and what happens? It is interacting with this one. Okay, so when it is interacting with this one, let's say I am talking about a very localized space, right? So here, let's say my 300 volt is there, plus 300 volt is there. However, now that this distance in a bulk scale, in this distance, right, the bulk scale distance was 5 centimeter. That is why 300 by 5 I was doing. Okay, but now what will happen if I am talking in terms of a localized scale? Then this localized scale, what will happen? This distance, this will be a very this distance will be in the order of, in the micrometer or in the order of nanometer, right? So whatever this voltage was trying to accelerate this, all this macro or the large amount of scanning secondary electrons from a bulk scale, if I go to a very small scale, then here what will happen? In this case, if you divide this micrometer, let's say 300 volt divided by some micrometer I am dividing, that means this electric field which will be generated in just on this surface, if I am considering, when the electric field will be generated, it will be in the, let's say, in the order of 10 to the power 5, 3 to 10 to the power 5 volt per centimeter, right? So the electric beam is coming, and when it is interacting with a very small amount of area in my specimen, then here the electric field which is generated now, here this electric field is in the order of, that means my plus 300 volt is generating electric field, local electric field in this area, then again in this area, then again in this area, then again in this area. So if I am talking in terms of localized electric field, right? So when I am talking in terms of localized electric field, then it will come in the order of 10 to the power 3 to 10 to the power 5 volt per centimeter. Now we have a problem, and this does not happen in a regular basis. This only, I am assuming that this will happen in a very localized scale, that means in the nanometer level. Okay, so when I am getting, you see here I was earlier getting 60 volt per centimeter, right? This was my electric field here. Now I am getting an electric field in a localized electric field in the order of 10 to the power 3 to 10 to the power 5 volt per centimeter. Now what will happen? Since the electric field on the surface, just above the surface, you can consider that just above surface means almost touching the surface, here it's a very high positive electric field, right? So here it's a very high positive electric field. Here, however, if I am talking in terms of detector, here this detector is pulling them, let's say some 60 volt per centimeter electric field. with a force of this one, right? Since at that time what will happen, though I am repeating again, this amount of electric field which is happening between and with the amount of 10 to the power 3 to 10 to the power 5 volt per centimeter, it is a very localized reaction. It is a very localized analysis, right? So what will happen here, I am having on the surface, I am having a very high positive electric field. Here in the detector I am having some amount of positive electric field. So at an instantaneous time, if I want to, at any time if I want to check what is so now what will happen, the beam comes, interacts with the specimen, and all the secondary electrons will be coming out. In this scenario, in this particular scenario which I am mentioning it this side, so secondary electron will be coming out. But at this instant, the electric field here, it is very highly positive electric field, and this electric field in this section will be very higher than the electric field in this section, right? And due to that region, the secondary electron which was earlier supposed to go and hit all this detector, right? All the secondary electron was supposed to go and hit the detector, so that we will be ideally we should be getting a higher secondary electron coefficient, right? That thing we will not be able to get, right? So this is what I have written it here, electric field as a result of externally applied potential. Externally applied potential, we are getting it here, right? And local electric field increases in the 2 orders greater than ET electric field. ET electric field means the electric field which is applied by this detector, right? Since local electric field here, it is increasing to many orders as compared to this ET electric field, the emission of secondary electron will be little bit slow, right? And since this emission of electrons will be little bit slow, we will not be able to get all these specimen. We will not be able to get all the secondary electron of this specimen, right? So that is why sometimes what will happen, the secondary electron, since they will in some areas, right, in some of the areas when secondary electron will not be able to reach the detector, that means those areas will be having a darker region, right? And in some area where the secondary electron are able to go, and this is a very small scale electric field. Whatever electric field it is pulling the secondary electron, it is a very small scale. So that is why even with this high amount of electric field, some of the secondary electron will be able to go, and they will be collected by the detector here, okay? So in whichever area the secondary electron goes in a less quantity, those areas will be darker, and in the area where the secondary electrons will be more, they will be collected in more amount, those will be in the brighter side, okay? Those will be in the brighter region. So eventually what you will get somewhat like white, black, then again this is black, white, then black, again white, then again black. So black, white, dark white. So this kind of band thing you will get, ideally you will get, but it depends on also on your microstructure. It need not be necessarily this one. You can also get according to, let's say this is your dark area, then again some dark area is there, this is your bright area, this is your bright area, this is again dark area. So based on whichever section your secondary electrons are coming, this electron you will get your microstructure based on dark and some of the dark region and some of the brighter region. That is why, since the main factor which is creating this darker region or this brighter region is voltage, because due to this voltage only we are getting the electric field here. So this type of contrast is also known as voltage contrast, okay? And yeah, so due to we can say that this electric field contrast, whichever is occurring, it is occurring due to the difference in surface potential, right? Let's say in one portion of the surface the potential is more, then it will attract more secondary electron, and it will not allow all the secondary electron to go to the detector. Let's say in some of the surface the local electric potential is very high, or very low, then it will allow this secondary electron to go and is will be collected by, those things will be collected by the detector. So since voltage is the manipulating factor here, so this kind of contrast mechanism is known as voltage contrast. Okay, so since it is happening in a very localized scale, it is not able to affect this kind of so this kind of mechanism is not able to affect the whole the bulk mechanism. So that is why it is a very weak contrast. And so the normal mechanism, the normal detector mechanism, whichever I showed it here, so this is the general mechanism. This is a, considering this factor, this electric field mechanism, we can see this contrast mechanism considering that we are calculating the electric field from a very, very small region. Okay, and then comes magnetic field. So we know that also there are different types of magnets are there in our material system. And why the magnetic field is there? Because since electric the incident beam is carrying electrons, and electrons are negatively charged. Okay, since electrons are negatively charged, so they will be having like, let's say incident electron beams are coming, they are experiencing some amount of force when they are coming through a magnetic field, right? So that force is given by F is equal to E V cross B, right? And due to that, from a direct path, they will be coming first to spiral path, then again they will be coming helical path. So this was the reason. So now if we are saying that the negatively charged particles are coming through a magnetic field, which are staying in the pole piece of our scanning electron microscope, that column, that electron column. So when it will be experiencing the magnetic field, an amount of one force will be acting on this incident electron beam. So that logic we can also extend to the material as well, not only to the pole piece which is staying in the objective lens or the condenser lens, but that same logic also can be applied to the material. How the material? Because we know that there are materials like cobalt is there, nickel is there, iron is there. So these kind of materials are magnet, and there are also different magnetic these are the natural magnet I am talking about. So there are different types of synthetic magnet which are commercially also made. So those kind of magnets are also there. That means they will also have some amount of magnetic field associated with them. So now when the electrons which are which are negatively charged beam, electron beam which are carrying negatively charged particles, when those particles will experience the magnetic field of these materials, what will happen? They will also experience some amount of force, right? And this, so that will also affect some amount of, that will also give some amount of contrast to our microstructure. To see what is the amount of contrast it will impart on our microstructure, we also need to study this contrast mechanism, right? And we know that the magnetic spins of certain atoms aligned over large region. So this thing is called as, in magnetic material, this thing is called as domain, right? So in a large region, like if I am talking about a large region, right? So let's say my magnetic moment like this, if I am talking about magnetic moment, okay, so over it, so what is the magnetic spin? So this kind of material based on the magnetic field, so this is one domain, this is another domain, this is another domain. So like this, based on their magnetic spin, I can say that this whether this material is magnetic or whether this material is ferromagnetic or ferrimagnetic or antiferromagnetic, right? So based on this thing I can say. So I know that in materials domains are present, right? And these domains contain highly directional magnetic field, right? Based on this orientation of these domains only, we can say that whether a material is eligible for a magnet or not, right? And when these domain intersect the free surface, let's say I am having a material here and these domain impart a magnetic field, right? Let's say like this, they impart a magnetic field. Then what will happen? Then when this is my surface, when this domain intersect the free surface, then there are some amount of leakage, so what will happen, they will pass through free space. It is not necessary that entire magnetic field will be constrained inside the material, they will pass through the free space as well. Okay, so these are the, let's say these are the free space. So these, when this magnetic field crosses this surface of the material and passes through the free space, then what will happen, then the creation of, here we can say the creation of leakage field will take place, right? So the creation of leakage field will take place, and when this creation of leakage field take place, let's say my incident electron beam is coming, and this is a negatively charged particle, and here when it will, since these are the leakage field are there, right, already, that means magnetic field are produced due to this magnetic domain. Okay, so when they will be interacting with this field, let's say in this direction they will be interacting with this field, then in that case some amount of force will be acting on this incident beam, as well as, because the amount of force which will be acting on this incident beam, though those will be the force when we derive that force, or when we see what kind of force is there, so there the velocity will be considered for the backscattered electron. But since there are magnetic field, so there are two types of electrons we know. One is BAC, which is related to the incident beam, right, and another one is AC, which is related to the specimen. So when both of them are having different velocity vector, right, if I am talking like VAC, here also I have to talk like VBAC. So since both of them are having two different velocity vector, electric field is there, charged particle is there, so the force imparted on them by this magnetic field or by this leakage magnetic field will be different, and due to that our collection will also vary, the collection by the detector will also vary. So that is what will impact, will produce another contrast mechanism, that is due to this magnetic field. And these since one is AC, one is BAC, so two types of magnetic contrast mechanism is there, one is type 1, type 2. So this type 1 contrast mechanism is related to AC, that means secondary electron. This type 2 contrast mechanism are related to BAC, that means backscattered electrons. Okay, so we'll see what type 1. So here the type 1 means the interaction of secondary electron after they have exited the specimen surface with the leakage magnetic field, right? So when they let's say I am saying, so this will be my magnetic field, this will be my magnetic domain, okay, and my beams are coming, right, and due to the leakage magnetic field, so this is electron beam, this is electron beam, and let's say my I have put this my secondary electron, so these are my secondary electrons going, these are the AC. Now this I'm only talking of the secondary electrons, I'm not talking the backscattered electron. We'll see what will happen to the backscattered electron as well, but for now I am considering only secondary electrons. Since my secondary electrons are just going out and interacting with the leakage magnetic field, so the force will be F is equal to minus E cross V. So here V is velocity vector of SC, that means secondary electron, and B is the magnetic field. Magnetic field will be same, because for a material magnetic field is decided by the amount of magnetic how many magnetic domains are present. So magnetic field will not change, electron charge will not change, but since velocity vector I am talking about, that means I am talking about the magnitude as well as I am talking about the directions, right? Since these two things will change, that means my V is also, secondary electron will also change. So now that magnetic field is there and some amount of force is acting on my secondary electron, that's what I know now. So if those force are acting on my secondary electron while going, let's say my detector is this, right, while just leaving out the surface, if the amount of force which is acting on my secondary electron is bringing them towards the detector, then that region will be looking bright region, right? When my the amount of force which is acting on my secondary electron is taking them away from the detector. That means I'm not able to collect as much secondary electron as I wanted to collect from this region, let's say region 1, region 2 and region 3. So the amount of force that my secondary electrons are experiencing from region 3 is driving them away from this detector here. That means this region will be darker region. Okay, and since this bright region and darker regions are coming in between, I will be able to see the contrast. And same thing will also happen for 2. If my secondary electrons, the secondary electron whichever are coming out of this surface is, if they are going towards the detector, then that region will be I can see those region as bright region. If they are going away, then I can see them as dark region, right? And for this, since I am talking about, always remember, since I am talking about the secondary electron, for secondary electron my detector should be Everard only detector which is positively biased. Okay, and when I am talking about BSC detector, backscatter detector, then in that case same ET detector I can use which will be negatively biased. The ET detector is not only used for secondary electron, it is also used to collect the backscatter electron as well. Okay, so this is the type 1 magnetic field, right? Then coming to the type 2 magnetic field, which is coming due to the backscattered electron. Backscattered electron are the electron which were earlier coming with the incident beam, right? Since incident beam, how they become the backscattered electron? When the backscattered electron, they are scattering, like one is elastic scattering, another one is inelastic scattering. Okay, so backscattered electron, they are also electrons. They might be having a large amount of energy, but they are also carrying a negative charge, since they will be interacting with the so the effect of internal magnetic field on the incident beam, right? Since they will be coming, let's say this is my material, okay, and this is the incident beam IB I am writing, and in such a way I am my detector is here. Okay, so this type 2 type 2 magnetic contrast arises effect of the internal magnetic field. That means, let's say my domain is lying some my material is giving me some amount of domain. That means my domains are almost aligned. Okay, they are not not misaligned to each other, they are almost aligned. That means this is a magnetic material that I am talking about. Let's say my force will be in such a way that it will my incident beam is coming, and due to the magnetic field inside my material, the force will be in such a way that it will allow my magnetic this incident beam to go further and further, that means penetrate deep into the material. Eventually this material, due to the energy of this backscattered electron beam, the incident beam which will be coming out as a backscattered electron beam, eventually they might come out of my material, but they will be a little bit the penetration depth will be a little bit more if the my magnetic field inside my material is allowing them to penetrate deep into the material. Then in that case my backscattering electron yield, which I am talking about eta, that will decrease, and in that case I will get a darker material, darker region, right? Similarly, let's say so here I am drawing, okay, let's say this is my material, okay, okay, I'm just tilting my material a little bit so that the space will be there. So let's say this is my incident beam is there. Now my detector is there. It can happen also to a flat specimen. I'm just drawing so that it will be convenient to put the detector here, so that you can visualize. So this is my incident beam, right? Electrons are negatively charged, but my electric field, let's say internal electric field, my internal magnetic field of my material is applying force on this beam in such a way that it is not able to penetrate deeper into my specimen and immediately coming out as backscattered electron. And since it is not able to penetrate deeply into my material, then in that case my backscatter electrons will be, number of backscatter electrons will be more, and my backscatter coefficient eta will be high. So this region I will get it as brighter region, right? So that is how I will be able to get the contrast, like bright contrast, dark contrast. And so it is this is the type 2 kind of contrast that I will get. And so to get, and remember, the maximum contrast that I will get here is not this contrast is almost, if I am talking about cobalt, nickel, or iron, this bright region and this darker region, if I am talking in terms of percentage, the maximum contrast in an iron, strong iron magnet, I will get it as 0.3%. That means it is very, very less. So though I am saying that I will get a darker region, I will get a brighter region when I am talking about magnetic contrast, but in a strong magnet which is made up of iron also, if you are talking natural ferromagnet, the maximum contrast between, if you are seeing between bright and dark region, you will be able to only get 0.3 contrast, which is very, very low. It is kind of a weak contrast, you can say. So that is why you can so seeing this quantification, you can see this contrast. This is one of the weakest contrast mechanism, but it is a special contrast mechanism when we are talking in terms of the magnetic material. And to get this kind of this 0.3 kind of contrast, 0.3% contrast as well. So this is, I am talking, so 30 kV, that means my voltage is also very high. Okay, since my voltage is also very high, my energy is also high. So in this case I will be getting this contrast. And to get maximum contrast using in a type 2 magnetic field, so 55 degree, so this specimen should be tilted, right? So specimen should be tilted to 55 degree from the horizontal. Okay, so this is the another kind of contrast, when this is another kind of special contrast mechanism, but it is one of the weakest mechanism, be it in electric field contrast or be it the magnetic field contrast, right? So now coming to the coming to the crystallographic contrast, this is also another type of contrast which is related to the arrangement of atoms. So earlier we saw the topographic contrast, then we saw the compositional contrast, which are strong contrast, then we saw two weak contrast, which are caused due to electric field and which are caused due to magnetic field, right? Now we will see another type of contrast that is known as crystallographic contrast, and this crystallographic contrast arises due to the principle. So this is the principle of this crystallographic contrast, that regular arrangement of atoms in crystalline solids can influence backscattering of electron, right? So regular, what do you mean by regular arrangement of atoms in crystalline solid? That is, if I am talking that lattice, right? So when I am talking that the lattice, the arrangement of lattice or the symmetry of the lattice also can influence the backscattering of electrons. So in crystallographic contrast, we are not talking about secondary electrons anymore. We are only talking about backscattering electron. Okay. So how this backscattering of the electron will influence? So let's assume, so see this picture. Okay, let's say this is my incident electron beam. Okay, so my incident electron beam is coming, and this is also same my incident electron beam. Okay, since my incident electron beam, I am saying so you can ask that why my incident electron beam is, one is obliquely being incident on my sample, another one is parallel incident on my sample, because since we have known that we are using the aperture, we are focusing, let's say this is my sample, and using the aperture we are focusing some of the beams like this also. So that is why I am currently considering, so this is my objective aperture if I am talking. Okay, and since some of the rays will be oblique and some of the rays will be completely normal to the surface of the specimen, so that is why I am talking now that these rays, one ray is falling onto my sample like this, another set of rays are falling onto my sample parallelly. So what will happen in one case, this angle which are this, consider this red incident beam which are coming. So here when it is coming in this direction, it is experiencing, and now relative to the angle that this incident beam is coming, right, the oblique, the red incident beam is coming, when it will interact with my specimen here, let's say this is my specimen, when the red incident beam is interacting with my specimen, it will experience more atoms in its path, right? It will experience more atoms in its path. That means whether you, if you are taking in a plane, then you can talk in terms of atomic packing density, right? So that is or if you are talking in terms of a direction, then you can say linear packing density, right? So this beam, this red beam will experience more number of electrons in its path, right? And since it will experience more number of electrons in its path, then what will happen, it will start scattering immediately. Okay, since it will start scattering immediately, and these beams, these red beams which I am talking about, they are all incident beam, and these beams which will be coming out of, and this scattered beam, they will also be incident beam, since they have lost some amount of energy. So those will be the BSE beam, that means the backscattered electron beam. Okay, and when I am talking to the incident beam which is made up of this blue color, so this blue color incident beam, in its when it is going on this direction, in this direction, then what will happen, it will experience a less number of a very less number of atoms on it, in its path. So that means here for this blue color incident beam, the atomic density, okay, on its path is very low, and the path where the atomic density are very low for an incident beam, so these things are called as channels, not the electron beam. Okay, so this where the atomic densities are very less, so these things are called as channels. Okay, so due to these channels, don't assume that this incident beam, okay, this incident beam will not be able to scatter. They will be able to scatter, but since these channels exist, channels means low atomic density, okay, areas or directions where low atomic densities are found, since due to the existence of this channel, this blue electron beam will be able to penetrate deeper into the material, right? Since due to the penetration deeper into the material, they will be, now these red beams will be immediately collected, and the more number of backscattered electron will be collected by this red beam. But since they will be coming they will be penetrating deeper into the material, some of the electrons might lose their energy, and they will not come as equal as to this red beam, so they will also come out. Okay, they will also come out, but the amount of the backscattered electron corresponding to this blue beam, that will be very low as compared to this red beam. So since this contrast which is arising is because of the channel, so this crystallographic contrast is also called as electron channeling contrast. Okay, so this and here also the contrast that is happening, and means which the beam which is experiencing high atomic density on its path and the beam which is experiencing low atomic density on its path, they will be giving contrast. But still here also the contrast of the contrast between the brighter region, and that means this red beam will give you, so I'm writing it here, so the red beam in the down, so the red beam will give you brighter contrast, and the blue beam will give you a little bit darker contrast. Since the contrast arises due to the channels, so that contrast is called as electron channeling contrast, and the contrast amount, if I want to quantify the contrast between maximum or the brighter region and the darker region, will be around 5% difference, though it is it is also a very small contrast. Then you can say why, like if these channels are there, then why the small contrast are coming, because the grain orientation, here I am talking about a single orientation grain, right? When we talk about a multiple means a polycrystalline single orientation means it's a single crystal. When we are talking about multiple orientation, that means a polycrystalline material, then the contrast that arises from one let's say arises from one section of one grain will be cancelled out by another section of another grain. Okay, so due to that, so let's say one brighter region is there, so high number of backscattered electrons arrive at the detector. Then similarly in another section, low number of backscattered, so if I am talking in terms of like this, okay, so when I am taking just a second, okay, so when let's say here I can draw this so that you will be able to understand. Let's say here I am getting more backscattered electron, here I am getting less backscattered electron, then again I am getting more backscattered electron here, okay, then again I am not getting more backscattered electron. Then all these backscattered electron, when I am now in this direction, my backscattered electrons will be large, in this direction my backscattered electron will be large, so they all tend to cancel out each other. Okay, in a bulk scale they all tend to cancel out each other in the 3 dimension. So that is why the contrast that I am obtaining in a single crystal is not the same contrast that I will be able to obtain in a polycrystalline sample. So giving an example to that, let's say this is my single crystal, since all the grains are oriented in a particular manner. Okay, so this is my single crystal, and when I am trying to scan the single crystal, let's say let's assume for now that this is a very large single crystal and I am scanning, let's say these are different kind of beam. Okay, I am scanning from one beam to position number 1 to position number 7. I am scanning, so in between this thing there will be some angle. Okay, before that, then how this scattering phenomena will occur, we will see just a little bit, we will just go a little bit into that. So the scattered, so to know or to determine the likelihood of this electron channeling, whether we will get the contrast due to this electron channeling, the properties of electron beam, that means we should know what with which wavelength our electrons are coming. So the properties of electron beam, or basically if I want to say lambda, then it has to be so it is related to the critical crystal property. So what do I mean by critical crystal property? I am saying in terms of D is the interplanar spacing, because these channels are related to the atomic density, right? So atomic density means I am talking about plane, so here interplanar spacing. Okay, so the properties of electron beam, if I am talking in terms of lambda, that means if I am talking in terms of lambda, I am eventually talking in terms of the energy. So the property of electron beam, if I want to determine the likelihood of scattering, I want to relate with the critical crystal property. So how will I relate these things? So these things will be related by a famous equation that is called as Bragg's diffraction equation. Okay, this Bragg's diffraction equation, we will study it in XRD in the subsequent weeks. So this equation tells that n lambda is equal to 2d sine theta. So I am writing theta as theta b. Theta b is the Bragg's angle. Okay, so here, so lambda is the wavelength of the electron beam that is coming. N is the order of diffraction. So here I am saying the order of diffraction, but when we will be studying Bragg's law, we will be saying order of reflection, because Bragg's law is an oversimplified version of the diffraction law, and here the Bragg's law is derived considering reflection is happening, considering the atomic planes are acting as a mirror. Okay, so there we will consider the reflection, and considering the reflection we can also say that the order of reflection. So lambda is the wavelength, so here D is the interplanar spacing, and theta b is the Bragg's angle. That means it is certain angle theta only. It is not always true that any incident beam will be scattered by the atoms in the material. No, it is the incident electron beam has to come at an angle of theta b. That means a Bragg's angle it has to come, then only it will be able to scatter. Okay, so when this condition n lambda is equal to 2d sin theta b it matches, then only this scattering will happen, and then only this backscatter, the yield in the backscattered electron, whereas in some portion the yield will be more, in some portion the yield will be less, right? So the contrast will come. Now coming to this diagram, here some of the between, since this electron beam is scanning from point 1 to let's say point 7 with the beam 1 or with beam 1 to beam 7, so it will be scanning a large amount of area. So if my electron beam is scanning a large amount of area, then there will be some theta b, that means the Bragg's angle, where the scattering will take place, right? So when I am talking when I am talking in terms of scanning the electron beam, then some amount of Bragg's and Bragg's angle will be there. So, according to the when this Bragg's diffraction equation, when it matches with the Bragg's angle, then the diffraction will happen. And remember, those diffraction, the planes which will be diffracting, those are called as Bragg's plane. Okay, I am writing it here. So those are called as Bragg's plane. Okay, so this will also, what will it do? And when this kind of contrast will arise, then when the backscattered electron will go and they will create a series of lines. So some angle in this thing, right? Since it's a single crystal, and some of the incident beam are creating a Bragg's angle or are being incident on a Bragg's angle onto this crystal, then the diffraction will take place. And since the diffraction will take place, then what will happen? Then the channeling contrast will.
I'm sorry to just interrupt you. Just sorry.
Yes.
I need a small clarity that Bragg's law, where X-ray falls, there in lambda 2d sin theta is applicable, correct?
Yes.
Now here electron is falling.
Yes.
And also here we are talking about in lambda is equal to 2d sin theta.
Yes.
So both are the scenarios are different. How this Bragg's law is applicable here? Can you please elaborate?
Okay, Bragg's law is actually based. So Bragg's law, when we are talking about Bragg's law, it is just that how the scattering is happening, right? So Bragg's law is based on the the condition. Bragg's law tells us the condition of diffraction. So diffraction is a part of the scattering. Scattering can happen in all 360-degree, and when a certain condition of scattering is fulfilled, then only the diffraction can happen. So Bragg's law is derived according to that. That means it will give us the condition where the scattering becomes the diffraction. So same thing here also can happen, that let's say these electrons are coming, and while interacting with other atoms, or we can say other electrons, there also scattering phenomena takes place. So in that context, when we say that here the electrons are coming as well, so when these are different kinds of electrons are there, or the atoms are there, so when they will be interacting with this electron, then the scattering phenomena will take place. So since scattering phenomena will take place, then from scattering, how we can go to diffraction? Then when the Bragg's law, this law will be satisfied, then only. So here that is why this lambda will be of the electron wavelength that I am taking. Okay, and the d that we are talking about, this is the distance between different planes. So interplanar spacing. Since I am talking in terms of scattering now, so that is why Bragg's diffraction equation I can put here. Is that solved? Did that clarify?
It's okay. I I understand that scattering point you are talking.
Yes.
But still, I remember this thing that X-ray falls, then it is applicable. Now, when electron falls, then Bragg's law for electron surface, it is applicable. That is my main point.
No, X-ray also falls. See, X-ray also falls. That means a certain amount of energy, or the beam, let's say beam of photon falls onto an atom, and then it reflects back. That's what
I'm putting other way around. Then thing is that Bragg's law is applicable for when electron falls on this scenario happen. Similar cases also Bragg's law can be applicable.
Okay, yes, the
That's
thing
why
is,
it is like
okay. So why I told the scattering phenomena is, so we have to go a little bit deeper into the X-ray. So the thing is, the Bragg's law we are, the Bragg's law is an oversimplified version of the actual diffraction law. So the actual diffraction is the scattering happens actually. So actual diffraction, when you talk about in terms of X-ray, so there is another diffraction called Lowest diffraction. Okay, so there is another diffraction called Lowest diffraction, which actually tells us the different scattering that will happen when an incident beam, let's say that incident beam is currently photon, we are in X-ray, we are considering that incident beam is photon, and when an incident beam falls onto your on your material, then this incident beam can be scattered in all directions. And since this Lowest diffraction law, so based on Lowest diffraction law, there are 12 parameters for scattering. Okay, so this is the real diffraction law which was proposed by the scientists. But the disadvantages of this law is that there are 12 parameters in the scattering phenomena, and all those 12 parameters we have to know if we want to see whether a diffraction is happening or not. So that is why this Lowest diffraction, which is actually based on scattering phenomena, this has been oversimplified by Bragg's equation. So there are three Lowest diffraction law is there, Lowest first law, second law and third law. When all the three laws are simultaneously met, then only the condition of diffraction will take place. But this law, this Lowest diffraction law, has been oversimplified by Bragg, which has been given to us that when the beam of energy falls onto a material and the reflection or the scattering happens, then that will be, so we are considering currently the Bragg's law in a two-dimensional manner, but this Lowest diffraction has told us the scattering in a three-dimensional manner. So considering that factor, when an electron will encounter another electron in this material, in a grain, so there will also scattering phenomena takes place. So based on that scattering phenomena, if we are going to put this Bragg's law into we can always put the Lowest diffraction condition, that means the Lowest scattering condition, but that will complicate the so then we have to see the so there will be formation of we'll see in the X-ray diffraction that there will be formation of different type of spares will be there, like cones formations will be there, and so based on that, actually the scattering phenomena is not explained by the Bragg's equation. The scattering phenomena actually is explained by the Lowest equation. Since Lowest equation need 12 different parameters for us, because in three dimension we need 12 parameters to see whether this scattering phenomena is giving any diffraction or not. So to eliminate those complications in a two-dimensional visualization, we are assuming that the Bragg's law will take place. But this incident electron beam, this one as well as this one 1 and 2, they will not be diffracted, they will be first scattered. So we have to talk in terms of scattering. If those scattering will eventually go for diffraction condition, then we are assuming this simple Bragg's law equation.
okay, I got the clear. So left side picture we should not talk about the diffraction, only scattering will talk, and right side you just have the understanding.
So basically scattering can happen in 0 to 360 direction, but diffraction cannot happen in 0 to 360 direction. That's what my point is. So scattering, so diffraction is a subset of scattering. So any scattering we are talking about, we have to talk about in 3 dimension, which has to be given by Lowest equation. But since we are talking in terms of a 2-dimensional image, so this 3-dimensional equation has been actually simplified by Bragg's equation. And since from scattering how we will go to diffraction, so it has been given by Bragg's law. So first, since I talk about the scattering of this backscattered electron, so how they influence, and it is not necessary that all the scattering will lead to diffraction, but some of the scattering will lead to diffraction. And how we will give those equation will be given by Bragg's law.
Okay, thank you.
Yeah. Okay, so due to that we will get, so some of the electrons will be okay, we are here. So now that the beam is scanning across the sample of a large single crystal, so some of the angles will also be be there, which will follow the Bragg's law, and in that condition, so the diffraction will take place, right? So that is why we will be getting a series of lines. So these series of lines that we will get, it will be we will be able to see those series of lines in a single crystal. However, okay, so yeah, this is an example of this thing, the how we are able to get this crystallographic contrast. So this is an example of the series of lines. So this is for a single crystal. Okay, but now let's say some of the planes are oriented in certain direction in one crystal, and in another crystal those planes let's say in one crystal as 100 planes are not oriented in according to the Bragg's angle, but in another in the another crystal which is under a polycrystalline sample, in another crystal 100 planes are oriented in according to the Bragg's angle. So what will happen, the contrast that arises due to the single crystal in one section will be cancelled out by the contrast in the opposite section. So that is why in a polycrystalline sample we will not be able to get clear series of lines when these lines will be when these, so this is a polycrystalline sample, I think of nickel or something. Okay, so this is so this is a single crystal where we are able to get a series of lines which we can see, and here this is a polycrystal, here we are not able to see a clear series of lines. Okay, and yes, some of the here some of the features of the crystallographic contrast, why we see, because the degree of channeling, some of contribution of channeling in arbitrary orientation in a polycrystalline material, since arbitrary orientations are there, so that is why the degree of channeling will also will be added up, and that is why the channeling tend to cancel each other. So when they tend to cancel each other, the contrast that we are supposed to get, let's say if that material is an amorphous material, will be the contrast will be same everywhere, but here since a crystalline material is there, so there would be some contrast when we are with respect to the average contrast that we are getting from an amorphous material. And this is a very the electron channeling contrast is a very weak channeling contrast, because maximum it will give 5% contrast, as I mentioned it before, and 5% contrast when we remember the previous contrast mechanism, when we are remember the contrast definition, then the contrast should be minimum 5% for our eyes to detect any distinct features in a microstructure. Earlier we have seen, and taking consideration into practical difficulties of our experimental setup, we have also told that 5 to 20% contrast should be there for our naked eye to clearly distinguish. But here this electron channeling contrast, the maximum that we can get is 5%. That means 0 to 5% contrast will be there. So that is why this is also another weak channeling contrast. So that is why we have to increase the current for a frame rate. So this is an experimental parameter that we do generally. 10 nanoampere for a frame rate we have to increase the current. And since the backscattered electron will be after scattering based on their incident Bragg angle, after scattering, since they will be going in all of in many directions, so we need a large solid angle BSE detector. So this kind of solid angle BSE detector generally kept in inside the lens, that means through the lens detectors are kept. And so what do so that a large amount of backscattered electron even after the scattering we will be able to collect them. And this channeling pattern, the definition of channeling pattern is series of lines because of intersection of the crystal planes with the surface. Okay, so these are the some features about the crystallographic contrast mechanism. Okay, and using this crystallographic contrast mechanism as well, we can determine what is the strain and what is the plastic deformation that is taking place in our material. So here if you see here, it's a diamond indenter. After the diamond indentation, some plastic deformation has happened. Okay, just change the color. Okay, so these are the diamond indentation for. Okay, so after diamond indentation, these are the plastic deformation, and this, due to this plastic deformation, the defects can be introduced, and in that area some residual stress will also be imparted to the material. So this is a ductile material. The material I think is nickel. Okay, so yeah, so we will be able to see the plastic deformation, as well as we will be able to see the residual stress pattern in a ductile material. So this thing, this is a another. So here this is a, I will write, this is a plastic deformation, we will be able to see, and another thing we will be able to see residual stress patterns also we will be able to see. So here some strain map also we will be able to see. This is also after plastic deformation. So what is the residual strain? So this image, what are the residual strain are there? So this is a deformed polycrystalline we have taken. So deformed polycrystalline. So I think this is some alloys of iron. Okay, so deformed polycrystalline when we have taken, so in different direction, what is the amount of strain is there, we will also be able to see. So using the crystallographic contrast or channeling contrast, we will be able to determine these things. So now coming to the final section of our scanning electron microscopy, that is called electron backscatter diffraction, or in short we know it is EBSD. Okay, and why we need to see this electron backscatter diffraction? Because we know to get a complete picture of any material, these two are important. One is crystallography, another one is microstructure, right? So how the crystallography and the microstructure are related to each other, because these two things we need to know to see the structure property relationship, right? The structure property relationship tetrahedron, which we have seen in the first lecture, that what are the structure, what is the property, how it behaves, that means how it is giving performance, and what is the process. So the structure property relation of any material, if we want to link them, then we can if we want to know them, then we will be able to know by knowing crystallography as well as microstructure of a material. So that is where this electron backscatter diffraction or EBSD comes handy in an SEM in a scanning electron microscope, right? So the function of EBSD, or the information that we will get from the EBSD, as this we can identify any phase, whether any phase different, whether it's a single phase material, whether there are multiple phases are there or not, and then we can, the most important thing is we'll be able to see what is the orientation of each and every grain. Okay, orientation determination and phase orientation, and from this orientation determination we'll see there is another term called misorientation. So what is the misorientation also between grains, we will be able to see. And here one term is called as texture. So texture is individual orientation of a group of contiguous grains, right? So texture, in simple word if I am telling, then texture is preferred orientation. Preferred orientation means, let's say I am talking about my grain. So my grain is in, this is one of my grain, that means all of my grains are oriented in this direction. If I am, so this is a single crystal, right? If I am talking, let's say in a polycrystalline material, some of the grains will be oriented like this, another set of grains will be oriented randomly. So there would be no so this is a polycrystal. So this is a single crystal and this is a polycrystal. Now what is texture? Texture I said is preferred orientation. Preferred orientation means, let's say my so here, though I can see in this one, in this scenario, though I can see not all of the grains are oriented as per my single crystal, but they are oriented more, most of the grains are oriented more or less like single crystal, like this single crystal. They are not exactly oriented like that, but a little bit tilt, if we little bit rotation we do to this single crystal, they will be looking like this single crystal. So this grain and this grain, they all are oriented like this single crystal. That means in one direction my most grains are oriented, I can see, right? So this is known as the preferred orientation. That means not every grain is oriented in that that direction, but most of my grains are preferring to orient themselves in that direction. So that is what I call as texture. So texture is nothing but preferred orientation. Okay, and since this EBSD is a very useful tool to determine texture, so that is why we also use this EBSD to get orientation relationship between different grains. Okay, and we can also get some additional information from our sample, that is crystal plane spacing, that is angle between planes, crystal symmetry. All of this information we will be able to get from EBSD. Okay? And there is another term called microtexture. Microtexture is population of individual orientation that is related to the sample microstructure. So that means if I am getting a texture kind of, if I am getting here, let's say this is not the total sample, this is only an area of the sample I have mapped. So from here I have got a texture orientation towards, let's say 100. Okay, if I am getting a texture orientation towards 100 plane, then how if this 100 plane is correlating with my bulk material, my entire material, which is, let's say my entire material is like this, and out of those entire material, when I mapped one single material, then the texture information that I got, it is correlating with the entire material. Okay, so this section, the small section is correlating with my big section, big material. So that is why, that is when I will say that this is a microtexture. Okay, and then there is another term called mesotexture, that is the misorientation between the grains is termed as mesotexture. So these are some of the terms, and EBSD. Okay, so yeah, so here we will see. Okay, and here we will see how the electron backscatter diffraction takes place. So here a highly tilted specimen is illuminated with a, remember here, a stationary electron beam. The beam does not move, like we do not start scanning the beam like we do for an image. We rather keep the beam stationary and then we tilt the specimen in different direction, and we tilt the specimen in very small angle to view the different kind of diffraction that is happening. So remember here it is diffraction happening, right? So we are no more only viewing the image, but also we are getting crystallographic information. Crystallographic information comes from the symmetry of the material, and the symmetry is decided by the position of the atoms in their lattice planes. Okay, so all those information we will be able to get from EBSD. Generally this tilting degree is 70 degree. That means beam is coming like this, and so let's say beam is coming like this. My material will be, if I am talking, okay, it will be tilted somewhat like this. So the in 2D inside view, if I am talking about, this is my 70 degree. So this angle is 70 degree. So this is my specimen and this is my beam, the small one. Okay, this is my specimen, this is my beam. So now if I am talking about, so my beam is coming, and here one cone kind of formation will be happening, because my beam will be, after interacting with the material, the electrons will be scattered in all direction. All means backward as well as forward. It is not necessary that the electrons will be always scattered in forward direction. Some of the electrons will also start scattered in backward direction. So this is a two-dimensional picture I gave, but this thing also will take place in all the three dimensions. So when the beam comes, this is my material is here, and then I will be able to at 70-degree angle, a tilted specimen is illuminated with a stationary electron beam. Then the beam interacts with the specimen and then finally inelastically scattered. When I capture this inelastically scattered electron beam using a phosphorus screen, and that screen I generally keep very close to this thing. So this is the schematics of a electron backscatter diffraction. So same electron SEM column that we put, but only thing here different is that the beam is stationary, but the specimen is tilted to a very high level. That means 70 degrees Celsius. 70 degree. And another reason why I am able to extract so much information from electron backscatter diffraction is that the resolution is very high. It is in the order of you can say 10 nanometer, the resolution of the EBSD, right? So if my resolution is in the order of 10 nanometer, then I am able to get information from the crystal structure of the material, right? And the angular the resolution also, angular resolution, if I am talking about, then the angular resolution is also in the order of it is less than a degree, okay, less than 1 degree the angular resolution. So that is why electron backscatter diffraction will give me very very good, though I am using same backscattered beam, the backscattered electrons for extracting result, but the resolution will be much more higher than what I would have otherwise got from my backscattered electron, right, using backscatter detector. So here I am getting the information using diffraction, okay. And so there are two types of information, two types of EBSD is there. One is conventional EBSD, another one is transmission Kikuchi diffraction, TKD. So conventional EBSD uses a bulk sample at a steep angle, same like 70 degree angle, and backscatter electrons are detected. So this is a conventional EBSD which you have done. Only thing necessary for one EBSD is your sample preparation. For EBSD, generally the sample preparation should be as good as possible, because first we have to polish it using normal emery sheets, then we have to go to diamond paste polishing, then we can if required we can go to alumina or colloidal silica polishing, that is sub micron level. Then finally if any scratch marks are there, then we will be able to finally we do the electro polishing. So after doing the 3/4 layer of polishing, then finally without any scratch marks we will be able to produce the scratch free surface, which will give us the EBSD, in this kind of pattern we will finally get. So this is so here in this kind of pattern we will be able to extract information regarding phase, regarding crystallographic orientation, regarding interplanar spacing. So we will be able to we'll be able to extract and we'll be able to also see what are the orientation relationship, also we'll be able to extract. And now that we know that this is a different this is an EBSD pattern, so what we will do, we currently we are seeing a series of lines are there in an EBSD pattern, and these lines are called as Kikuchi lines. Here we are seeing the Kikuchi diffraction, so these lines are called as Kikuchi lines. Okay, in an EBSD pattern, when we first put our sample, we see that whether the Kikuchi lines, these kind of Kikuchi lines are coming according to the crystal symmetry or not. Then accordingly we vary different we go to different map, different section, and then we finally map the material to get the information. Now coming to the Kikuchi line, so we'll see what Kikuchi diffraction is. So Kikuchi diffraction is which we'll get all these Kikuchi lines due to the Kikuchi diffraction. So what does that Kikuchi diffraction and why it occurs? It occurs when low density of defects are there and the thickness. Now there is two types of diffraction happening. So Kikuchi diffraction will give us the lines. Here we saw the lines are we are able to see different set of lines here, right? So Kikuchi diffraction will give us lines. But however, if normal diffraction, let's say I'm talking, so when this Kikuchi diffraction happens, when the thickness of the material is high. High means when the electron cannot completely penetrate the material, or the thick material is there, so that electron so the penetration depth of electron is around 100 nanometer, right? So when the material is thicker than that, then in that case the diffraction will take place. And when the material is thinner, in that case we will be getting the diffraction will happen. In that case we will be getting spot diffraction. Okay, and when the material is thicker, we will be getting the diffraction that will be taking place is Kikuchi diffraction, which will give us different lines, and those lines are always parallel, and one line will be bright line, another line will be dark line. Okay, and so here thin diffraction will give us spots and thick diffraction will give us lines, and this thick diffraction is related to the Kikuchi diffraction. So it's a quantitative microscopy. There will be two lines. I will tell why those two lines will come. One line is known as excess line, another line is known as deficient line. Okay, and we do the by viewing the Kikuchi pattern, we see where one of the most important okay, so one of the most important information when we go to the transmission electron microscopy is we derive, there is a term called zone axis. So by viewing the Kikuchi line, we will be going to our zone axis, because in transmission electron microscopy, this zone axis is one of the most important parameters to see any kind of structural features. If you are not at the correct zone axis, you will not be able to see your features which you are trying to see. So going to the correct zone axis, it is only possible when we know how our Kikuchi pattern is coming, whether the pattern that we have got, whether it is correct pattern or not. When we will be getting this correct Kikuchi pattern, then deciding that whether we have got the correct Kikuchi pattern or not, we will be going to our zone axis, and finally we will be able to see our different structural features. So now this Kikuchi line, so yeah, this is so why this Kikuchi diffraction takes place. So far we have assumed one thing, that electrons are coming, and let's say this is a sample, electrons are coming, and whether it's elastically scattered or inelastically scattered, we have assumed that if it is elastically scattered, then it is elastically scattered everywhere. If it is inelastically scattered, then it is inelastically scattered everywhere. But this kind of diffraction happens when this incident beam is coming. Okay, when incident beam is coming, when initially it interacts with your specimen, then it will inelastically scattered. Inelastically scattering takes place. The first scattering that will be taking place, it will be inelastically scattered. Then the next scattering that will take place, this also there is a possible. Okay, this is elastically, so scattering by elastically. Okay, so the first scatter when the electron beam will be first inelastically scattered and followed by elastically the electron beam will be elastically scattered, then there will be diffraction pattern generated, that is known as the diffraction pattern. Okay, and if we want to see, I am doing it here, let's say intensity versus let's say scattering angle. If I am talking, then the curve will be somewhat coming like this. So this is angle, scattering angle, okay, and this is my intensity here. Okay, and now when my scattering angle versus intensity, inelastically scattering intensity if I am talking about, then this is like this. And whatever I have shown it here, all those 1 2 3, these are all Kikuchi pattern. So we'll see here one can see that this line is a bright line corresponding to that line. So this line is a relatively dark line, right? So similarly there are bright line here corresponding to that, this is a dark line. So we can see that there will be pair of lines which will be dark and bright, pair of lines will be there. So why they will be there, we'll just see. So if my intensity, if my incident electrons are only inelastically scattered, then I should have got this kind of structure, right? But now since that it is elastically scattered, after the inelastic scattering it is elastically scattered. Let's say I am taking, this is my specimen. This is my screen I am talking about. Let's say first my incident beam is coming, okay, and these are different types of planes are there, okay. Now this diffraction at point P, this is my incident electron beam, okay, and this is my specimen, and my specimen I am considering two plane. So first I said that this will be inelastically scattering, and then I said that followed by inelastic scattering there will be elastic scattering. Elastic scattering I am talking, when I am talking, that means it will only change its direction. So here I am considering that this scattering which will occur, so it will after inelastic it will occur by following the Bragg's law, okay. So this thing I am assuming. Now this point at point P, it will be first inelastic scattering happen. Let's say inelastic scattering happen. Looking at this picture, my incident beam can scatter in all 0 to 360 direction. So my
Sorry, again, just interrupting you.
Yes.
In between, just inelastic scattering and scattering by elasticity. Can you repeat
No,
it
it
again?
is like inelastic scattering, and here since I have written scattering first, so it is elastic scattering. That's all. Since,
Inelastic and elastic. Okay.
yeah, since I have written scattering by elastically, so with scattering first, so that is why I have written this one. So one is inelastic scattering, another one is elastic scattering. And in elastic scattering, I am considering that my scattering is occurring due to Bragg's diffraction law. Okay. So now at point P, first inelastic scattering is happening. Now looking at this specimen incident electron interaction, my after scattering my beam can move in all directions. So one will be coming like this, another one will be coming like this. So let's say these 2 points are, I am considering one will be Q, another one will be R, right? And if I am talking in terms of, so this is the normal, okay, and these are the two planes I am talking about. So at point P, my first scattering will be inelastic scattering. At point Q and R of these two planes, my scattering will be elastic scattering. I am now considering that the elastic scattering is happening due to Bragg's law. Okay, so what after scattering here elastically, so what will happen? It will go like this, right? This beam has been elastically scattered and my screen is capturing this one, okay. And similarly here also one elastic scattering will happen, and after this my beam will also fall on this one, right? Let's consider this point as S, let's consider this point as T, okay, and this point as O, right? So ideally in inelastically so this angle, now that I have considered my elastic scattering is happening in terms considering my Bragg's diffraction law is satisfying, so this angle will be 2 theta, okay. So now what will happen, this one, this beam which is coming and falling onto on a point of T, ideally this beam was supposed to come in this directions, right, after inelastic scattering. Similarly this beam also, it was supposed to come and fall in this direction. So I am naming this beam as IS and naming this beam as IT, right? So now what will happen, this whatever the intensity, if I want to let's say intensity of this beam is IT and intensity of this beam is IS. So at point S, if I am talking point S, the intensity is increased by IT minus IS, right? If I am talking, that means at point S ideally the intensity should be IS, but now the intensity is increased by IT minus IS. If this diffraction was if this diffraction would not have taken place, right? So at point S the intensity will be increased by IT minus IS, and then at point T the intensity will also be increased by IS minus IT, right? So in this case what will happen, now we know that if by calculating, by considering that these planes would not be there, so looking at intensity of T and looking at intensity of S, intensity of S will be greater than intensity of T, right? So in this condition, this intensity of T minus intensity of S will be a negative quantity, right? And intensity of S minus intensity of T, it will be a positive quantity. Since this will be a negative quantity, this will be a positive quantity, this curve which was supposed to come like this after inelastic scattering, this curve will become, this is the scattering angle, this curve will become like this. It's more or less like this. It's a hump. So it is a well, and this is a hump kind of structure. It's a distribution, normal distribution. So the intensity curve, so this is the point S, this is the point T. So the intensity curve which was supposed to come like this is, let's say I'm talking about the ideal intensity curve. So here the practical intensity curve. Okay, that means at point T the intensity, there will be a hump kind of, the hump means there will be excess intensity. So the intensity should be like this dotted region, but there is an excess in the intensity. So this is what is called as an excess line here. Okay, or you can say here it is a bright line, and this is what we call it as, since intensity was supposed to be this dotted line, but it is a well kind of structure, that means down in the intensity. So corresponding to this one, this will be a dark line always associated with it. Since after inelastic scattering, this elastic scattering takes place, and this I am talking only in terms of a two-dimensional object, but this thing will occur in a so if you rotate this thing, let's say if you try to rotate this one, if you try to rotate these two lines along this axis, then it will be a conical structure formation will you can see, and that conical structure formation, okay, this is the last concept, and that conical structure, so those cones are called as Cosell cones. Okay, and when those conical structure, when those cones will be intersecting another sphere, another terminology that I am using, that sphere is called as Ewald sphere. This concept we will study exclusively in X-ray diffraction. So when these cones when these cones will be intersecting this Ewald sphere, then only these two lines kind of thing will be coming. Actually these are not lines, actually these should be two parabolas. This perpendicular this pair of lines that we are seeing, they are actually parabola. But since when these parabolas are intersecting the Ewald sphere, and the Ewald sphere is so large, these parabolas are we are viewing this parabola as pair of two straight lines. So these kind of bright dark combination we'll see, which are known as the Kikuchi diffraction. And yeah, Kikuchi diffraction, if we tilt the specimen a little bit, let's say this angle, if I am talking about, this is the camera camera distance, camera length I am talking about L. We'll see what is camera length in diffraction when we are indexing the diffraction. So there is a distance called camera length L. Then if we tilt the Kikuchi diffraction even with an angle alpha, then the total lines will be moving at a distance of L alpha. Let's say I am talking in terms of delta, the lines will be moving like this. So tilting the specimen will get different Kikuchi lines, and by indexing those Kikuchi lines, that means these lines are this line is related to a certain set of planes. Okay, and the distance between these things we will be able to see how much 2 theta, that means the Bragg's diffraction, how much Bragg's diffraction has occurred, and using those things we will be able to see we will be able to measure the orientation of our crystal. Okay, so yeah, that concludes our session. We'll go through a few of questions, so a few numericals are also there. We'll try to solve those things. So that brings us to our first question. The first question is, what is the minimum grain diameter for EBSD imaging? Okay, so can anyone answer? It is related to, I told, related to the resolution of the EBSD. Okay, we have discussed this in our class.
Option B, sir.
Yes.
So B sir, 10 nanometer.
Yeah, so that is the correct answer. So because the resolution, it varies actually, it is not exactly 10 nanometer, it is sometimes 10 nanometer to 30 nanometer. In certain cases also it can go up to 100 nanometer. That means if you use a very good like FESEM, okay, FEG source if you use, and then if you do the EBSD imaging, then you will get the minimum diameter we will be able to resolve is 10 nanometer. Okay, yeah, this is also another question related to EBSD. So the question is, spatial resolution of the EBSD is about to statement 1, for high resolution imaging, for high resolution imaging on nanograins, high performance FESEMs are required along with a small sample, short working distance. Okay, I don't know spatial resolution. So okay, the question is, out of this three statement, which one is the correct answer for considering the spatial resolution of our EBSD? Okay, so the statement 1 is saying that for high resolution imaging on nanograins, high performance FESEMs are required along with a small sample and short working distance. Can anyone answer? Okay, so it is related to the spatial resolution of the EBSD. So for high resolution imaging on nanograins, yes, since the nanograins we are talking about the resolution of the EBSD in the order of 10 nanometer. So if we want to determine the crystal size or the orientation relationship on nanograins, then we will be able to do it using EBSD. High performance FESMs are required. Yes, high performance FESM, because I told in the last question that the resolution can go up to in some cases 100 nanometers. So we need high performance FESM to image the nanograin, so that the spatial resolution will be increased. Then short working distance. Why? Because the short working distance means your probe size will be very low. That means the last class, if you remember, the working distance when we are increasing, let's say this is how our working distance was. Let's say this was our working distance. Okay, if we increase the working distance instead of S1 to S2, then the probe size will be this much, so which is not a ideal condition for mapping. Okay, so in this case short working distance. So related to spatial resolution of EBSD, all three are correct. For high resolution imaging nanograins, we can do EBSD. High performance FESMs are required because for nanograins the size will be in the order of nanometer, and then we'll be needing high performance FESMs. And since short working distance will eventually give us the diameter, the less probe diameter, so we are that will also increase our short working distance will give us less probe size, that will also increase our spatial resolution. Okay, yeah, so this is question number 3. What is the first step for sample preparation for the EBSD measurement? So this is related to, I think, sample preparation in any of the it is true for all scanning electron microscope, optical microscope, as well as transmission electron microscope. So option A is sectioning, option B mounting, option C is grinding, and option D is mechanical polishing. So which one will be the correct answer?
Yes, sir. Sectioning.
Yes. So for any of the sample preparation we want to do, first we have to section the sample. That means we have to cut the sample according to our dimension, according to our required dimension. Then only we will be able to then we mount the sample after let's say my sample is in some random shape, then I have to cut the sample in a particular direction so that it will be convenient for me, as well as whichever direction I want my microstructural information to get it from. So then after cutting the sample, then only I'll do the mounting. Then after mounting, I'll do the grinding. If I need to move a large amount of material, I will do grinding, or if I need to move a small amount of material, like very fine material, if I want to remove, then I will do polishing, then etching. So that is how the common sample preparation is for scanning electron microscope, and that is also true for this EBSD measurement. Okay, so this is a numerical question. So the question is telling that an accelerating voltage of 20 kV applied to the tungsten filament in SEM, what could be the wavelength of the electron? So voltage is 20 kV, so it is asking about wavelength. So what would be the wavelength? Can any one of you calculate? So you can use for hint I am saying you can use the de Broglie, you can combine the de Broglie relationship, and you can use the energy and wavelength relationship, and yeah, you can combine those two. Then also you can use the relativistic mass that I told a few classes back. Those things also you can use, and then finally you can get. Okay, so we'll go we'll solve this question. So earlier I told that using the speed of light and means correlating the speed of light with our velocity of electron, then we have to take consideration of the relativistic effect. When we are talking in terms of relativistic effect, then mass will be m is equal to me1 minus, so this will be our mass, right? This is the effective mass of our electron, right? So this will be our effective mass of the electron, and finally so this will be m. Then the de Broglie wavelength, if if we consider the de Broglie wavelength, we know that, so from here we have a term called v, which is the velocity. Now this v is the accelerating potential, the accelerating voltage, right? So how we can connect this thing with that one? The momentum with the using de Broglie relationship, we know that lambda is equal to h by p. This will be giving you h by m into v. So this v is the velocity, right? And now we know that when the energy energy gained by the electron when it is traveling at a speed of e will be equal to the potential energy, which will be ev. Here the v is the accelerating voltage, right? Here I can write it is a small v and here the capital V. So equating all these three, so in that case what will happen? So in that case, if this is the potential energy that I am talking about, then this will be half m into v square, right? In ideal scenario, here instead of m, when you substitute this m value, right? And here instead of m, if you substitute, then finally rearranging all these things, so this equation, and this equation, so rearranging all of these things, you will get a final equation. You will get lambda is equal to 1.5 divided by v plus 10 to the power minus 6 into v square, right? Yes, square and to the power this one whole to the power 1 by 2. No, this is 1.5 into 100. No, okay, this is 100 will be there. So when you take it out, so this equation eventually become 1.5 divided by v plus 10 to the power minus 6 into v square to the power 1 by 2. So the final expression that you will get, I think somewhere close to 150 divided by 1.5 by 100 equal to 150 divided by v to the power 150 divided by v. So this will be your final expression, right? So why I have written this expression instead of this one? Because in this term, in the v square term, you can see, so in the v square term it is 10 to the power minus 6 is there, so we can neglect this term, this second term. When we neglect the second term, this expression is becoming 1.5 divided by v to the power v square. So when we take both of them into square, we can so this is 1.5 is there, here 150 is there, nothing different is there. In one case, here you will get the answer in angstrom, here you will get the answer is nanometer, that's all. Okay, so finally we have to use this equation 1.5 divided by so considering that this value is very small, in the order of 10 to the power minus 6, 10 to the power, so this is the value that we have to use for lambda. So the some nanometer it will come. Can anyone calculate what will be the nanometer? So 1.5 divided by square root of and this v, whichever I am telling, so here in this case this v will be in the kilovolt, here this v will be in the volt. You have to consider that thing. So these two equations are eventually same, only thing is that here you will get answer in angstrom, the v will be in the kilovolt, here the v will be in the volt. So volt means here it is given 20 kilovolt. So when you consider 1.5 divided by 20,000 root over, the value will be coming in 0.0106.
Sir, option B.
Yes, this is the option. Okay, so this is the formula. So this is the I am writing here. So lambda is equal to 1.5 divided by v plus 10 to the power minus 6 into v square, right, entire 1 by 2. This is your actual formula considering relativistic effect. The equation, this is equation 1, this is equation 2, this is equation 3. considering 1, 2, 3, you will get this equation. But now this 10 to the power minus 6 is there, so we neglect that thing, and from here we will get the value 1.5. This value we will get 1.5 divided by v to the power 1 by 2. So that will be your lambda. Okay, and here the v is the accelerating potential. Okay, so this is another conceptual question related to EBSD. What is steps necessary to produce? Okay, this is not there. What steps? So this. So what steps are necessary to produce an EBSD pattern in an SEM? So statement 1 is tilt the sample so that its surface makes an angle about 70 degree with the horizontal. Turn up the scan coils to obtain a stationary electron beam. Place a recording medium in front of the tilted specimen to capture the diffraction pattern or the phosphor screen. Okay, so which option would be correct? 1 only, both 1 and 2, both 2 and 3, all of 1, 2, 3. Which is the correct option? Can anyone answer? This is, I think, related to how we are generally obtaining an EBSD pattern. So these statement 1, tilt the sample so that its surface makes an angle 70 degree with the horizontal. That means highly tilted electron and specimen will be interacting with the stationary electron beam. So this is correct. Turn up the scan coils. What is the role of scan coils in the scanning electron microscopy column? It is to deflect the electron beam, right? Whether if the electron beams are diverging, then the role of scan coils is to deflect the electron beam. So turn up the scan coils, that means we are not deflecting the electron beam anymore. That is how we are able to achieve this stationary electron beam, because stationary electron beam is needed so that only it will interact with the highly tilted specimen. And finally, place a recording medium we have to capture. So this is the yes, this is what this phenomena. So this is beam is coming, stationary beam, and then phosphor screen will be there to capture. Okay, and only thing added here is the scan coils are turned off, because the role of scan coils are to deflect the electron beam. So the option D will be correct option. Okay, so yeah, this is another numerical question. In an electron microscope, the electron beam of wavelength, okay, 0.0061 nanometer passes through an electromagnetic lens of having strength 0.T. So here this has been given as B. B is 0.6 Tesla. T is the unit of Tesla. Calculate the radius of electron beam. Can anyone calculate? Okay, I will so lambda has been given, right? So lambda has been given means we can easily, we know that lambda is equal to not considering the relativistic effect, 1.5 divided by v to the power 1 by 2, right? Here v is the in volt. Okay, so this, from here we will be able to get the accelerating potential, right? When we get the accelerating potential, if you remember in the lectures, the professor has told about the radius of the electron beam when it interacts with the magnetic field, right? After electrostatic lens, there is another section was when in the introduction of electromagnetic lens. So the radius of the radius of electron beam that was calculated, that formula was given by, let's say I am talking R of electron is equal to, the formula is given by 1 by B and then 2 mv divided by E. So this is the formula. So here B is given, m here refers to the mass of electron. Mass of electron is 9 into 10 to the power, I think 9.1 into 10 to the power minus 31 kg mass of electron. Charge of electron 1.6 into 10 to the power minus 19 coulomb. Here V is the voltage in accelerating voltage in voltage. So E is known, M is known, B it has given, V was unknown, but V we can calculate using this equation from lambda is equal to 1.5 V by 2. So this is also known. By putting all these things, we will be able to calculate Re. So can anyone tell me what is the value of Re? I don't have a calculator. 1 by B. Okay. Anyone? Okay. So yeah, I don't have a calculator now. So this is the value that which will give you the value of Re. I don't know which one is the correct answer. So using this formula, you can calculate which value you will calculate. Okay. So we'll go to the next question. Next question is, the primary electron beam current is 1.5 micron. Secondary electron current is current signal is 0.4 microampere. The backscattered electron current signal is 0.6 micron. What could be the sample current secondary backscattered electron? So okay, so the primary electron current is this. So here what would be the sample current secondary and backscattered electron yield? Okay, so here I'll tell the total beam current is given by, let's say, I secondary plus I backscattered plus ISC. This is the sample current. So from here you will be able to calculate what is the value. So here I naught, the primary electron beam current is 1.5 microampere. Secondary electron current is 0.4 microampere plus backscattered electron current is 0.6 microampere. They are asking what could be the sample current. So sample current, let's say I am talking in terms of sample current now. So 1.5, this is 1. So sample current will be 1.5 microampere minus 1 microampere. So it would be 0.5 microampere. Now they have asked what is the backscattered electron yield. So backscattered electron yield, I told that current related to the backscattered electron divided by total current. Let's say total current, I am writing it as now I naught. So what is the backscattered current? It is 0.6. Total current is 1.5. So what will be the answer? 0.6 divided by 1.5. It is 0.4 coming. So this is 0.5 and 0.4. So B will be the answer. Okay. So this is an equation you have to take into consideration. Okay, and then question number 8. Yeah, so the question is, the angular accuracy of EBSD related to EBSD is how much? 0.5 to 1 degree, 0.5 to 1.5, 1.5 to 2, 1 to 1.5. So how much will be the angular accuracy? Can anyone tell? I have discussed this in today's class.
Sir, yes, sir.
So angular accuracy is of EBSD will be 0.5 to 1 degree because it is below 1 degree. So that is why we are able to see any grain orientation, misorientation also we are able to see. Okay, this is a conceptual question. And okay, so the Kikuchi lines consist of, and this in a diffraction pattern, the options are excess line, deficient line, both of the above, reflected line. Can anyone answer?
C.
C, sir. C.
So Kikuchi line will be always consisting of two pair of the lines. That means one excess line and another one will be deficient line. Okay, so there are a few more questions are there. Choose the correct option. Statement 1 is channeling contrast comes due to backscattered electron. Okay, and statement 2 is backscattered electron coefficient is dependent on the orientation of a crystal with respect to the electron beam. Okay, so the options are 1 only, 2 only, 1 and 2 are correct, but 2 is the correct explanation of 1 and 2 is the correct explanation of 1. D is 1 and 2 both are correct, but 2 is not the correct explanation of 1. So channeling contrast we studied. Can anyone answer this one?
Sir, C, sir.
Yeah. Okay. So here the statement 1 is channeling contrast comes due to backscattered electron, and we know that depending on the orientation of the crystal, the backscattered electron will vary, because whether it's a single crystal or whether it's a polycrystalline material, accordingly the backscatter will vary when the channeling phenomena takes place, right? So based on that orientation, so the coefficient, since the number of backscattered electrons that our detector is going to detect vary according to the orientation of the crystal, the backscattered coefficient will also vary. That means statement 1 is correct, statement 2 is also correct. So this is the correct statement 2 is the correct explanation of statement 1. Choose the correct option. Step size in EBSD should be less than the grain size. Statement 2 is each grain gives particular orientation. So what will be the 1, 2? 1 and 2 are correct. 2 is the correct explanation of 1. 1 and 2 both are correct, but 2 is not the correct explanation of 1. What would be the answer?
C.
1 and 2 both are correct. 2 is the correct explanation of 1. We'll see. No, I think D is the correct answer. Yes, D is the correct answer, because step size in EBSD, so this relates to the resolution of the EBSD, because step size in EBSD should be less than the grain size, then only we will be able to see what is the grain size and what are the relationship between the grain size. However, this resolution, each grain gives particular orientation. This is only related to the material. Each grain gives particular orientation. So this is actually the resolution of the technique we are talking about, and so this is the material. Both of the statement are correct, however. So but this statement 2 is not the it is not indicating that the statement 1 should be the it is not indicating to the statement 1. So the D option will be correct. Both are correct, but 2 is not the correct explanation of 1, because one is saying us about a technique, another one is the next statement is giving us information about the material. Okay, I think this is the last question. Which of the following statement is correct with respect to Kikuchi lines? Formed due to inelastic scattered electrons followed by elastic scattering. Formed due to elastic scattered electrons followed by inelastic scattering. Formed due to inelastic scattered electrons only. Formed due to elastic scattered electrons only. So option, which one is the correct one? It is related to the Kikuchi line.
Yes, sir.
Formed due to inelastic scattered electrons followed by elastic. Yes, so A is the correct answer. Rest 3 are not the correct answer. So first inelastic scattering happens, then only elastic. So the phenomena that we are talking about, that elastic scattering happens and then inelastic scattering happens, or inelastic scattering happens followed by elastic scattering. So this is called dynamic scattering, because multiple scattering event is taking place. Initially when we are studying, we always study that one kind of scattering phenomena, one type of scattering phenomena is taking place, but however when multiple scattering is occurring, those things are called as dynamic scattering. Okay, is there any other questions? No. Okay, so